starts with an earthquake, birds and snakes, an airplane. Lenny Bruce is not afraid.
Hello students, this is Mr. Ezra. Today we are going to talk about characteristics of polynomial functions, specifically the domain, range, and intercepts. I want to remind you that for some of the lessons there are guided notes available in your packet. For some lessons there are not. And with these characteristics notes, a lot of times I'm relying on looking at a graph or a picture, or there's lots of text on the page, and if you don't want to copy all of that down and there are not guided notes available for you, check the Moodle. In Moodle there might be a link to the PowerPoint version of the presentation that I'm using, so that you can kind of print that out if you want and add your notes to it. And if you want to take notes the old-fashioned way, just copying down everything you think is important and drawing and sketching the graphs yourself, that's fine. However you want to take notes, that's up to you. But I just wanted to make sure that you knew that that was available to you before we got started today. Well, with domain, range, and intercepts, we're going to be looking at a lot of graphs and trying to identify the domain and range of different polynomial functions. And then we'll be looking at both graphs and just algebraic functions written out to decide how to find the two different types of intercepts. And as we do this, we're going to have to review a few things, like how do you represent things in interval notation, and what does an intercept look like, and what are other words that I can use for intercepts. So kind of pay attention to the vocabulary that we use as we go through this, and hopefully we'll be able to brush up on the things that you need to brush up on, and you'll have no problem with this concept. So first, let's talk about interval notation. Remember, when we want to write interval notation, for example, we have here x is less than 2. Well, we use both brackets and parentheses for interval notation. You might remember that from earlier this year or years previous. When you want to include the number, you use a bracket. If you want to say, well, this number is part of my solution set, use a bracket. And if you want to exclude the number, in other words, you're going to say, this number is not part of my solution set, but my solutions start here at this number, you'd use a parentheses. Well, when x is less than 2, well, first let's draw this on a number line. We basically have an important number 2 on our number line. It's an open circle, and we're shaded to the left. So what we're basically saying is, everything to the left of 2 is our solution, but is 2 our solution? Well, no, it's just less than 2. It's not less than or equal to. So we want to exclude 2, but represent everything to the left of 2. You write these intervals from left to right, or least to greatest in this case. The least is way over here, forever to the left at negative infinity, and the highest that we go, although we're not including it, is 2. So our interval in interval notation would be from negative infinity to 2. Now remember that infinity and negative infinity always get a parentheses. They never get a bracket because it's not a number that you can include. It's basically kind of like a direction that we're traveling forever towards or forever from, but it's never a destination that we can reach. So it always gets a parentheses. It is never included as part of the solution set. And in this case, 2 is not included either. Let's look at another one. This time we have negative 4 is less than or equal to x is less than 9. So let's start on a number line. The two important numbers on here are negative 4 and 9. So I'm just going to put those on there. On negative 4, we're basically saying here that negative 4 is less than or equal to x. If you were to read that backwards, we would say x is greater than or equal to negative 4. That's a closed circle on the negative 4 and a shading to the right. And then we've got here that x is less than 9. Well, that's an open circle on the 9. It's not included, and we're shading to the left. So this is an intersection problem. We want to know that, or we understand that our solutions are between negative 4 and positive 9. Now, do we include the negative 4? And because it says or equal to, we are including the negative 4, so it gets a bracket. We are not including 9 because it says less than 9. It's not 9. It's everything that's to the left of 9, but greater than or equal to negative 4. So 9 gets a parenthesis. So as we start talking about domain and range, we want to remember that when we write things in interval notation, these are the things that we have to think about. Do we use a bracket? Do we use a parentheses? And how would we write our answer in interval notation? Now, when we talk about domain, we are basically saying all of the x values that are possible on the function or on the graph. And when we have a graph, we're going to read that graph left to right. We're going to look on the left side, and we're going to go all the way to the right side, and we're going to ask ourselves, what possible x values are there available to this function? For range, we're looking at all of the y values. Now, the y-axis is the vertical up and down axis. So when we're reading this one, you want to start at the bottom, which are the negative numbers, the lowest numbers. And we're going to look from the bottom to the top. We're going to ask ourselves the same question. What y values are available to this function? What y values is this function using? For example, we have here a function that starts at -1, -5, goes up. It has a vertex or a top highest point at 2, 4, and then comes back down to 4, 0. So where there's a closed circle here on this graph, it means that those points are on the function. But remember, an open circle is kind of like an endpoint that's not included. So 4, 0 is where this function technically kind of ends, but that point itself is not included in the function. The domain is going to be all of the x values from the left to the right. Well, we have the least x value is -1, and we have x values along this function all the way up to 4, but we're not including 4. So we would write this and say, well, we're including -1. Clearly, that is on the function. It gets a bracket. We have x values along this function forever until we get to +4, but because it's got an open circle, it is not included, and this is the domain of the function that's graphed. From -1 to +4, not including the +4. Notice that we don't care about the y values. We're just looking at the domain. We only want to know about the x-axis. Where is this function? What x values are available to it? Well, -1 is available to it. All of these between -1 and 4 are on the function itself. I have x values of that function. Well, what is the range of the function? Here, range is y values. So we're going to the y-axis and saying, okay, we're going from here, and our highest point, I know that we have the function ends over here left to right, but the highest point we have is right here at 4. We're only looking at y values from the lowest point to the highest point here. In this case, the lowest point is included, and the highest point is included. So the range is going to be from bottom to top, -5, all the way up to +4. -5 to +4. We're going to include both of those. It is mathematically correct, I guess. Good mathanese, good math manners, to put this from least to greatest. If you put on a test 4, -5, you're going to lose some points because your interval is in like the reverse order that it should be. It should be bottom to top, least to greatest. Well, with polynomial functions, when we start looking at them and seeing what the graphs looks like, there are not going to be dots at the end of the functions. They're going to be arrows. They're going to go forever in 2 different directions. Well, all polynomial functions have the same domain. It's always all real numbers, as long as there's not some limit on the domain because of like a word problem or something where the domain is limited. But if we have a pure polynomial function, the domain is going to be all real numbers. Now you can write that as a capital R with those two little vertical lines coming down on the left of the R, or you can write it in interval notation from -infinity to +infinity, but that's the only answer that we're going to see for the domain of a polynomial function. The range, on the other hand, sometimes is all real numbers. Sometimes there's going to be a lower boundary, and we're going to go from that lower boundary all the way up to infinity, including the lower boundary. And sometimes we'll have negative infinity all the way up to an upper boundary, and we'll have a bracket on the upper boundary. And we'll see this in some examples here. In just a little bit, we'll see this in some examples. All right, what is a zero? Well, zeros are basically x-intercepts, where the graph crosses the x-axis. And although the definitions for these words are all slightly different, when I ask you for a 0, or an x-intercept, or a solution, or a root, I'm technically asking you for pretty much the same thing. They're kind of synonymous. I want to know where the graph crosses the x-axis. Now, you'll see that I might write my answers a little differently depending on whether I'm asked for an x-intercept or a 0 or a root. But those words you're going to see, and they all mean the same thing. Where does the function cross the x-axis? So we look at this and I say, well, what are the x-intercepts of this graph? Well, the x-intercepts are where the graph crosses the x-axis, and technically, when we want to write an x-intercept, we are writing it as a coordinate, as a point. So the 2 places, the 2 points where it crosses the x-axis here are 1, 0, and 5, 0. Those are the x-intercepts. Now, if I ask for zeros, I'm asking for the same thing. But instead of asking for the points, I want to know, kind of like, what's really asking you for is what is the value for x when y is 0? And when y is 0, that's the same thing as an x-intercept because y is 0 here, and x is both 1 and positive 5. So here you can just list it as 1 and 5. Just as the numbers themselves. You don't have to list them as coordinates. You just say 1 and 5 are the zeros. Let's look at another example. Here we have x-intercepts. Now, I want you to pay attention to this. Do you see this bounce here? This bounce indicates what we call a double root. And what a double root means is it means that algebraically, if we were to solve this problem, a double zero, a double root, it means that it would be a solution 2 times. Kind of a weird thing, I know. So when we list the x-intercepts, even though this is only one x-intercept at -2, 0, I want you to go ahead and list it twice, anytime it bounces off the x-axis, and realize that that's going to be a double root, that it's a solution algebraically 2 times. If it goes through the x-axis, then it's only a solution 1 time. So -2, 0 is the same solution twice, the same x-intercept twice, and the one on the right is just 3, 0, just 1 time, because it only goes through it. Bounces indicate a double root. So when I'm listing out my roots, this is going to be a root -2, -2, and 3. Now, technically speaking, like, could you just write -2, 3 and be right? Yes, but when we begin to solve polynomial functions in the next unit or 2, we really want to pay attention and know that where there's a double root and what it looks like on the graph. So I want you to get used to anytime you see that bounce off of the x-axis, that means there's 2 roots that are the same, and list them both out. All right, here we have how many x-intercepts? 1 goes through 2, 3. We'll list those out as -1, 0, 1, 0, and 2, 0. But when we list them out as zeros or roots, remember these all mean kind of the same thing. We only put the numbers -1, 1, and 2. You don't have to list it out as a coordinate. You can just list it out as a number. Well, y-intercepts are where the graph crosses the y-axis, and that's a pretty easy thing to find usually if you have a graph. Just look on the graph and say, oh, it crosses down here. Now this is going 2, 4, 6, 8, 10, 12. So technically this point here is at 0, -12. So that's our y-intercept. 0, -12 has a y value of -12. We don't have any special names for y-intercepts like x-intercepts. You know, x-intercepts, we can call them roots or zeros or solutions, but for y-intercepts, it's just y-intercept, that's it. That's the only word, and we'll list it out as a coordinate on the coordinate plane where it crosses the y-axis. Where does this function cross the y-axis? Well, it crosses at positive. Again, these are going by 2, 4, 6, 8, 10 if you can't see on your computer screen or your phone or whatever you're viewing this video on. So this y-intercept would be at 0, 2. Since the scale is going by 2, 4, 6, 8, we can see that it's at up 2. So I'm going to list out the y-intercepts and the number of zeros first. And I want you to kind of look at what I'm writing and try to see if you can come up with a pattern for where I'm getting this information. And then we're going to talk about it in a little bit more depth. So the y-intercept for A is 0, comma, -1. And the y-intercept for B is 0, comma, 15. So I want you to look at that and see, can you decide where I'm getting those numbers from? And hopefully you're like, oh, Mr. Ezra, there's -1 and there's 15. And you're like, okay, well, I can do that. I know the constant term is my y-intercept. Well, let's talk about why that happens. I want you to remember that to find a y-intercept, you let x be 0. If I let x be 0 here, I've got 3 times 0 to the 4th power, which is 0, and 5 times 0 squared, which is 0 minus 1. Well, when you do that math, 0 plus 0 minus 1 is, got it, -1. The same thing here, -2 times 0 squared is 0. 3 times 0 is 0. 0 minus 0 plus 15 is, you got it, 15. So algebraically, we're technically plugging in 0 for x so that we can find the value for y when x is 0, which is our y-intercept. Well, with polynomial functions, what happens when you plug in 0 for x is the constant is the only thing that's left standing because everything else cancels out, becomes a 0. Okay, let's do the same thing with number of zeros. Okay, let's kind of start from scratch. I'll erase that. And we'll say the number of zeros for A is 4, and the number of zeros for B is 2. Can you find where I found those numbers? Well, hopefully you're like, oh, Mr. Ezra, I see a 4 right here, and I see a 2 right here. And you're thinking, oh, well, you're right. That's kind of where we can find that. It so happens that if you account for all the double roots and irrational roots and all the possible types of roots, that the number of zeros is the largest exponent. Remember, we call that the degree, okay? For these problems, if I ask you for the number of zeros, I'm really asking you for the highest possible number of zeros, and you're just going to go to that degree and you're going to say, oh, it's 4. Oh, it's 2. Okay, we'll see that in all of the problems that we look at. So let's look at this problem where we're going to identify domain, range, x-intercepts, and y-intercepts. Okay, now remember that if your graph goes all the way to the left and it hits the edge of the graph, there's an understood arrow there. Same thing here, understood arrow. So my domain, I've got an arrow on the left and an arrow on the right. I'm going forever left and forever right, which is why my domain is going to be all real numbers. Remember that you can also write that in interval notation by saying from -infinity to +infinity, which is all possible real numbers. The range, I'm going to start bottom to top. There's an arrow on the bottom, and I follow my function, and there's an arrow at the top. So that means that all y values are available on this function, or possible on this function. So it also is all real numbers. And you don't have to write it both ways. It's one or the other. You can also write it as an interval from -infinity to +infinity. For the x-intercepts, remember that this bounce is a double root, so it's going to count as a double x-intercept kind of. So -2, 0 and -2, 0. And it's going to bounce off there, and then it's going to go back up through 1, 0. So that is all of our x-intercepts. And for the y-intercept, it only crosses in one place down here on the y-axis at -4. So that's 0, -4. And that's it. Domain, range, x-intercepts, and y-intercepts. Let's look at another example. Find the following: domain, range, zeros, and y-intercept. Well, domain, again, arrow on the left. Follow it along, x values along this function forever to the right. Every single one of these will have a domain of all real numbers. But in this example, the range is not all real numbers because you'll notice that there is a lower boundary. nothing on this function goes below this point on the graph. And this y value here is at -4. So -4 is included, it's on the function, and we have y values forever up, forever. Right? All these y values from -4 all the way up past 5 are on this function somewhere. So we're going to put bracket -4, saying that the range is going to start down here at -4 and go all the way up forever and ever towards infinity, parentheses. The zeros on the graph are at -2 and +2. And remember, since it's not asking for an x-intercept, we can just list them out and say -2 and +2. We don't have to write it in coordinate form. The y-intercept is at 0, -4 down here, 0, -4. And that is technically supposed to be written as a coordinate, an x, y coordinate. Well, that's pretty much it for characteristics of functions, at least domain, range, and intercepts. You'll get lots of practice with this, and you'll get to wrestle with it. And if you have any questions, please ask them. I hope that you're very successful and that you like this and it goes well for you.